Welcome. Today we shall see a few more problems on the refrigeration liquefaction. In this, today we shall be looking into the Linde dual pressure liquefaction and Claudia refrigeration. First, let us take a problem on the Linde dual pressure liquefaction system. In this problem, the air is taken as the working fluid and it is operating between the minimum pressure of 0.101 megapascal and 20.2 megapascal, that is about 1 atmosphere and 202 atmosphere. Now, the inlet and exit temperatures for both the compressors are maintained at 293 K, that is the two compressors are working isothermally. The intermediate pressure is 3.0203 megapascal, that is about 30.3 atmosphere, and the intermediate pressure stream flow ratio, that is Mi dot by M dot, is about M.80, that is 80% of the main stream is being taken out for the the intermediate pressure. Now, we have to determine the liquid yield, the work per unit mass liquefied and the figure of merit, and we have to also compare these values for a simple Linde liquefaction system which is working between this minimum and the maximum pressure and at the same temperature. So, this problem will demonstrate how the use of a Linde dual pressure liquefaction system compares or improves upon the performance of a simple Linde liquefaction system. Now, just let us recapitulate first that how this dual pressure works, that we have these two compressors. So, this first compressor is taking the whole mass and it is taking it to the intermediate pressure, and the second compressor is taking to the final pressure. That means, here at point 1 we will be having that minimum pressure of about 1 atmosphere, and here we shall be having about 200 atmosphere, and in between we have that 30 atmosphere, and here we see that here we are getting the liquid withdrawal, and this is the TS diagram of the same system. So, here we have the initial pressure, the intermediate pressure and the final pressure, and these are the two isenthalpic processes. This represents this particular one and this represents this one. So, this we did earlier. So, I am not going into the detail of these explanations. So, let us now go to the problem. So, first write down all the conditions which are given to us here. So, these are the initial temperature pressure, this is the intermediate pressure and this is the final pressure, and T2 and T3 are also equal to T1 and T1. So, T1, T2, T3 are all the same. So, we have not written those things separately. Okay, temperature is constant. So, first let us look into the Linde dual pressure system, and in this the liquid yield is given by this particular expression. And what we have to do? We have to refer to the thermodynamic chart or thermodynamic table, whatever. So, we have seen those TS diagrams are given. So, you refer to the TS diagram and read out the values of the enthalpies from that TS diagram, and here are the values given for the various temperatures and various pressures. These are given. So, you plug in these values appropriately in this expression of the yield and find out the yield as 0.07. So, this is the value of the liquid yield. So, that means the 7%, that means if you multiply by 100, it will be about 7%. That means 7% of the total mass of the gas that has been compressed has gone into the liquid. Now, let us look at the work done per unit mass of gas compressed, and this is the expression for that. And again we find that here we have, in addition to the enthalpy values, we have the values of entropies. Even the entropy values have been listed in this particular table. So, what we can do now, we can plug in the values of the various enthalpies and entropies, and we get this as the work done per unit mass of the gas compressed. Next, we have been asked to find out the work done per unit mass of the gas liquefied, and here we have it that we take this value and divide by the yield, and we get this the value of the work done per unit mass of the gas liquefied. Now, we repeat the similar thing for the Linde's Linde's simple Linde system. Before that, we also find the FOM value, and FOM is the work that this W is the ideal work divided by the actual work, and ideal work can be given by this. This is we learnt earlier. So, the ideal work, we find the ideal work here, and we find this is the ideal work is this, and this is the actual work, and this. So, we see that this is this FOM is 0.239. It is quite low. Okay. Here we have the simple Linde system. Here we have that again only one compressor here, this heat exchanger, and the liquid reservoir from where we are withdrawing the liquid, and here is the TS representation of the same process. Again here we find this is we are doing the isenthalpic expansion here to get the liquid. Okay. So, for this we write down all the conditions, except that we do not need the intermediate pressure. Okay, we need only P1 and P3, and what we do all these things, and we again list out the values of the enthalpies, and we find out that liquid yield is this. And as we learned earlier that the liquid yield get a bit decreased due to this dual pressure system, but on the other hand we said that we gain something in terms of the work. So, let us see how that compares. So, first let us find out the work done per unit mass of the gas compressed, and here it is, we find that it is this value, and then we similarly we find out the work done per unit mass of the gas liquefied, and we find this is the value, and here also we find the value of the FOM like this. Now, after getting these all these values for the Linde dual pressure system and the simple Linde system, what we do, we put all these parameters in a table to compare them. So, here we find the liquid yield is given for the dual pressure system, which is a bit less than the one we are getting for the simple Linde system. Then with the work done per unit mass compressed, it is also a bit less than the simple Linde system. This work done per unit mass liquefied, this is also quite a bit less than simple Linde system, and this is the FOM value. FOM value we find it is a bit more than the simple Linde system. So, to understand that how much more or how much less, let us take a comparison of the percent increase or decrease. We find the liquid yield has decreased by about 15.6%. On the other hand, the work done per unit mass of gas compressed has decreased by about 51%. And the work done per unit mass of the gas liquefied has also decreased by about 42%, and the FOM has increased by about 74%. So, looking at these three figures, we find that it is quite justified to use a Linde dual pressure system, even though we have to sacrifice some amount of liquid yield. So, overall economics or overall decision will be based on all these parameters and just not on the liquid yield, and this justifies the use of the Linde dual pressure system. Next, we come to another problem on the Claudia refrigeration. So, here we have the Claudia, as we know that here we are using an intermediate expander to get further cooling, and here we have the 3 heat exchangers. So, here we have given the problem that we have a Claudia refrigeration system in which we are using nitrogen as the working fluid, and the gas enters the reversible isothermal compressor here. Okay. It is entering at about 1 atmosphere and 300 Kelvin and is compressed to 40 atmosphere isothermally. So, it is at point 2, it is 40 atmosphere and temperature remains the same at 300 K. Now, we have been asked to find out the mass flow ratio, this expanded mass flow ratio, that means how much fraction or total flow has been taken to the expander. So, this we have to find out, and we have been given the refrigeration effect that this is 80 kilojoule per kg, that is the refrigeration we are obtaining. This here means how much QA we are taking from here. This is the one which has been given to us per unit mass of the gas compressed, and the gas enters the reversible adiabatic expander at 40 atmosphere and 240 K. So, these are the given over here. Okay. Now, with these data, what we do, we first write out all the values which have been given to us, and what we do, we form this TS diagram. So this is the TS representation of the process, which I am not going into, and we know that it is working at this. This is the maximum temperature, this is the intermediate temperature, and at this temperature it is going into the expander, and this is the maximum pressure and this is the minimum pressure. Okay. So this way, and of course I told you that this dashed line is showing that it is a non-ideal behavior, but we are not considering that. We are considering the expander to be isentropic. So we shall be sticking to this straight line. So we, at these various conditions, what we do, we find out the values of the H1 and H1, H2, etc., and the entropy also. We know that the entropy at the inlet and the outlet of the expander are same, because we are taking them to be isentropic. Okay. So with these conditions, we find out we make a this first law of thermodynamics, we make a energy balance. That is the first here we do, and what we find, this is the energy balance over this particular control volume. Please understand that whenever you are making the energy balance, always remember to make the control volume. Without control volume, it does not make any sense to draw any kind of balance, mass balance, energy balance, etc. It does not make any sense. So first make out the control volume, only then you make these kind of balances. So we are making the steady state balance. So we get this thing. So this is this QA. This value is obtained from these mass flow rates and the enthalpies, and the enthalpy this flow rate into the expander, and the enthalpy at the expander outlet. Okay. So what we do, that we simply take this divide this equation by m dot. Okay. When we divide by m dot, so we obtain this, and this me dot by m dot is the x, which we have to determine. So we plug in the values of the various enthalpies in this equation, and we get this x as 0.4. That means we have to divert 40% of the actual mass flow of the from the mainstream to the expander to obtain this much, the given amount of the refrigeration. So this is how we are using this Claudia refrigeration cycle, and more details you may find out from these two references. Thank you.